Now, to move from multi-cell thunderstorms to supercell thunderstorms, we're adding in a rotating column. This does not mean that we're producing a tornado, because a tornado is a rotating column that comes down to the surface. Thunderstorms can rotate on their own up in the atmosphere, and that's what we're talking about now for a supercell thunderstorm. So, rotation, let's bring it on. And just to review, we have the setup for a lot of wind shear, and when it comes to a multi-cell thunderstorm, that wind shear becomes pretty dramatic, very dramatic. So we already have this cyclonic tilted back vertical structure. We already have a lot more wind shear in a supercell thunderstorm. Let's get into that a bit. We're bringing in a low-level jet into a supercell thunderstorm that will help us with the rotation. So when I say a low-level jet, I mean a low-level jet. You're used to a jet stream at about 300 millibars of pressure, up at around 15 kilometers. This is a low-level jet, and it's slower, but it's still potent at about 1.5 kilometers up. So in a rotating supercell, it's known for having a low-level jet in here that is usually right out of the warm, humid air that's convecting up from the maritime tropical air mass in the Gulf of Mexico. So in that case, what you've noticed here is that this is now an occluded front that has developed for a supercell thunderstorm, and now this is going to be either a cold occluded front or a warm occluded front. And in many cases, this can be a warm occluded front because this air mass that is in the warm sector is from the maritime tropical air mass out of the Gulf of Mexico, and it has some power to it during the late spring, summer, and early fall. So it can convect up, and it can be at a 40 or 50 knot speed up in that higher level. That will also bring down this downdraft and really solidify that downdraft as well. So you're creating more wind speed and more wind shear when you're doing this. And in creating more wind speed, you're really bringing in converging air into the surface high so that it's diverging out and changing direction with a stronger vector, with a stronger force. So that is one of the hallmarks of the supercell, is that low-level jet. And in doing that and bringing that low-level jet in, you are really setting yourself up to bring in the higher level polar jets or subtropical jets into that downdraft as well. So that now you can face what is known in European weather circles as a sting jet, which is a low-level jet that produces those really tough straight line winds during some severe squall lines with supercell tornadoes. But let's get back to the rotation a bit more. How do you get to that rotation? And why does the angle of the updraft change? Right? Just to go back a second before we really get into this, I had a backward sloping updraft in a multi-cell thunderstorm, and now suddenly I have a forward sloping updraft in a supercell thunderstorm. What's going on with that? Let's explore that a bit. When we are looking at rotation, I wanted to go into this a bit more with you. We set it up for an occluded front, and we set it up for a low-level jet. And look, I've got my upper level low to the west, so I'm providing all that nice diverging air with that low-level jet. And now look at this. The continental tropical air mass out of Mexico, off of the plateaus in Mexico, which are at a substantial elevation, comes in a little bit higher with dry, very warm air. So now you've got another change in direction that was from south to north. Now you've got southwest to northeast. You can start to see the air changing direction vertically as it's moving up vertically. So that's why I wanted to bring this in. You will get up to the regular short waves in the jet stream that can really strengthen the diverging air. Above it is the jet stream, which has been deepened by these short waves and takes off that diverging air even more. These storms can last for not days, but they can certainly last for 12 hours or so. They are different from the mid-latitude cyclonic storms that we studied just a week ago, but they have many similarities as well. We need to study a lot more about them. The wind shear is producing the rotation there. It is rotating with different speeds that are increasing and different directions that are changing. Just to go over this, and you can go over this slide, but I pointed out the low-level jet is the maritime tropical air mass. I pointed out that there is a dry air mass from Mexico, the continental tropical, which comes in at a higher altitude. I pointed out the short wave trough and the deepening of the long wave trough up here. I wanted to go into a little bit of the soundings again with you because, you know, I love soundings. And as these storms grow during the course of the day, the soundings change, obviously. So if you're in an area where they're doing, instead of 2 soundings a day, they might be doing 4 soundings a day, you can really start to see the vertical development of the storm during the day. This is during the morning when you have a relatively stable atmosphere. Remember, stable, steep environmental lapse rate, stagnant air that doesn't really climb far. Sometimes stratus clouds. These aren't stratus clouds, but these are not high cumulus clouds here. This is a stable atmosphere that was losing temperature as altitude increased, and then a warm radiant emission overnight warmed the atmosphere above and put a lid on this so that it will prevent a lot of cloud development during the morning. You'll see low cumulus clouds. Later in the afternoon, you'll get a lot more surface warming, and you might be able to mix things up a bit so that these clouds can start to grow in an atmosphere that isn't as warm as it was before because there's been more mixing with cooler air. So now we have a conditionally unstable atmosphere that is not quite as warm as it was before, and now through forced lifting and through latent energy, this parcel can stay warmer than the atmosphere around it and continue to grow. It'll stop up here where I have the continental tropical air mass moving in that is relatively warm. So during the afternoon, you have more fuel to mix up the atmosphere, but it might not go any farther than the continental tropical air mass, which is coming in out of Mexico and which is warm. So it's going to stop some of this development in many, many cases during the spring, summer, and fall. But in some cases, you have just so much latent energy in this warm, moist air that it can rise above the continental tropical air mass at about, I believe that is at about 700 millibars, and it can really explode up to the short wave and the long waves at the top of the troposphere. So that would happen later in the day when you've got a lot of surface heating that is emitting off and mixing this atmosphere and ascending and accommodating a cloud that is constantly warming and convecting upwards. Now, I've explained rotation to you, and I want to explain tornadic rotation from these clouds. So, tornadic rotation in 3 easy steps from a supercell and how that starts. So, tornadic rotation is noted at near the surface, and what you're seeing here is you are seeing a cold, dry air mass that is coming down from the polar regions, and it has been forcibly lifted a bit, and it can come around and be supported underneath by the warm, humid air mass, which comes around as well. These are not easy things to show, but you see that this is rotating and dropping down these clouds. Really fascinating, and it is rotating in that motion horizontally. When you have a low-level jet, that can come in and really accelerate all of that movement and all of that wind shear and go through that horizontal rotation at the low level in there. And then all you need is an updraft from some of these warm winds out of the Gulf of Mexico, and suddenly you've got a supercell thunderstorm that has turned into a tornado just on the impact of a roll cloud that was at the base of the supercell thunderstorm. So I wanted to point that out to you. And why does the tilt change in here? Well, the tilt changes for 2 very specific reasons. First of all, that tornado impacts the surface. So a supercell thunderstorm can rotate without coming down to the surface, but once this impacts the surface, it has all kinds of friction. It's tearing everything up. So it is slowing down the progress of this updraft at the surface. When this slows down, everything else is moving quite fast. It's going to take a forward tilt as a result of that. You can imagine the force that's associated with this to move that entire huge cloud in another direction. In addition to that, you will have a lot of precipitation and evaporation in this area of the leading edge of the cloud, up in the drier areas. So while you have a downdraft in the back, it is also possible to get a downdraft in the front where there is evaporation in the dry areas of the cloud that is producing a forward flank downdraft. And as that forward flank downdraft, it can pull down on the top of the rotating shaft and tilt it over as well. So you've got the surface dragging it, and you've got the forward flank pulling it. And that's how you can definitely change the entire dimension of a supercell thunderstorm and produce tornadoes out of it. I explained that to you, and I'll see you on the other side. I think we're doing lightning next.